So today, finally, we'll get to talk about derivatives around points on the eigencurve. So the goal is try to describe locally around some classical points with very explicit formulas for derivatives of the corresponding systems of Hecke eigenvalues. So let me just remind you where we left things off. So last time, we connected the geometry of the eigencurve around the point to the generalized eigenspace corresponding to the system of eigenvalues. So I'm going to look at the fiber over the weight x, and the system of eigenvalues of x in overconvergent forms. We, under nice assumptions, so for example, if I take the level of the corresponding form away from P to be exactly n, where n is the same level of the eigencurve, we have an equivalence between this being, the eigencurve being étale and this space being one-dimensional. So this is a nice characterization. We also said that to points of the eigencurve, we can associate a Galois representation. So for every x, I'm going to take QP bar points today, I can associate a Galois representation of the absolute Galois group of Q with values in GL2 QP bar, which is unique. Like, if I assume it to be semi-simple, it's unique. We said that this construction is a little bit indirect because what we are actually interpolating at classical points are the pseudo-representations attached to the various representations of classical modular forms. But then from those we can extract back at each individual point an actual representation, but they might not glue so well as a representation in families. So that's the issue. One thing that I want to point out that is important for our talk, for my talk today, is the conditions, the local conditions at P are a little bit harder to describe, but there is a special case in which this becomes quite explicit. So if I take x that lies in what we call the ordinary locus of the eigencurve, which is the locus in which the UP eigenvalue is invertible, so maybe denoted by slope less than or equal to 0, then the local condition at P is easy to describe. The property is that rho x restricted to the decomposition group at P is going to be up to isomorphism of the form. So something in the I'm going to say upper triangular, where the quotient on which we have the action by a character is unramified and carries the information of the value of the operator UP in the following way. So if I evaluate, since it's a ramified, I can evaluate it after being SP, and this is going to be equal to lambda x UP. Okay? This is called the ordinary condition for a representation, if you want. this is not so much a consequence of the construction of the eigencurve. This is really the theory developed by Hecke. So this was developed geometrically for Hecke families, but we can use it. Okay. Yes.
Is it easy to compare these two theories in the sense of when you get C smaller or equal to 0 to Hecke's construction of families, or is it by construction or is?
I wouldn't say by construction. The language of the constructions are pretty different.
Yeah.
I mean, it depends on what information you're trying to extract. So I think it's clear that you would see Hecke families in this language, so this should correspond to the rigid fiber of the Hecke's algebra. But yeah. Yeah, it's not even obvious that what you would get a priori, what you would get from Hecke families has to do with overconvergence, so there is definitely stuff to prove. Okay, so this is the setup. So the first thing that I want to talk about today is the work of Greenberg-Stevens. About the exceptional zero conjecture formulated by Mazur, Tate, and Teitelbaum. So these are things that we haven't introduced yet, and I won't introduce precisely, but I'm going to use this as motivation to explain that this type of results about derivatives, trying to compute derivatives of families, shows up when you're trying to prove some arithmetic formulas. So let me take E, an elliptic curve over Q. Well, split multiplicative reduction of P. So this is the crucial assumption. Then, by the work of Wiles, Taylor, Wiles, and so on, to this elliptic curve, I can associate a new form. So I can, the Tate module of this elliptic curve can be realized through modular form. So I'm going to call Fe, maybe just simply F, the way to new form corresponding to my elliptic curve, which, because of the split multiplicative assumption, will have level gamma not np with p not divided n. In this context, Mazur and Tate and Teitelbaum considered a p-adic function attached to E for the variable s in Zp. It's not going to be so important for us to see what this actually is, but it is constructed by using the theory of modular symbols that we haven't discussed in our perspective on the construction of the eigencurve. And from that point of view, it would have been more natural to consider an alternative construction of the eigencurve that uses the theory of called overconvergent modular symbols. Nevertheless, this guy arises by interpolating values at just s equals 1 but of the L function of the elliptic curve twisted by characters of conductors given by p powers. Anyway, so let's assume that we have such an object, and the idea is that the values at s equals 1 and like the order of vanishing and so on should also be related to the Mordell-Weil group, the rank of the Mordell-Weil group, and like in the non-p-adic case. But Mazur, Tate, and Teitelbaum observed that in this particular case, for the split multiplicative reduction, there was really a defect comparing the classical Archimedean case and the non-Archimedean case, which corresponded to presumably an additional order of vanishing of the corresponding L function that appeared because of an interpolation factor at s equals 1. So the observation of Mazur, Tate, and Teitelbaum is that there is this p-adic L function as constructed has a trivial zero in this setting. When there is a zero, one might want to make sense of a derivative, and they did some experiments and conjectured the following formula that was then proved by Greenberg and Stevens. So the theorem of Greenberg and Stevens is the following. So if I take the derivative of this p-adic L function at value s equals 1, I'm going to get something that is equal to the algebraic part of the L value, the classical L value, multiplied by what is called an L invariant. So, what is this L invariant? The L invariant in question is defined by, so, I'm gonna use the fact that now this only makes sense because of the multiplicative reduction. So I can use the theory of uniformization given by Tate for the QP bar points of my elliptic curves. An elliptic curve that realizes them as the quotient of QP bar units modulo a cyclic group generated by some parameter QE in QP of order p-adic valuation non-zero. And the L invariant is by definition the p-adic log of this guy divided by the p-adic valuation. Okay? So in fact, you could have taken any elements of this group to define this. That would have been fine. No, don't even need to take a generator. So this is, of course, phrased in a different language from what we've talked about so far. But the first observation that Greenberg and Stevens made is that this, computing this formula, the formula predicted by the Mazur, Tate, and Teitelbaum conjecture, is equivalent to determine a specific formula that involves something that is a priori not part of that picture, but corresponds to essentially computing the derivative of UP around the point corresponding to the form Fe on the eigencurve. So what is the point corresponding to Fe? So we are going to look at the system of Hecke eigenvalues of Fe because of the assumption that we have a multiplicative reduction. This forces the split multiplicative reduction forces AP of this modular form to be 1. This has p-adic valuation 0. So this is, if I look at the system of eigenvalues attached to Fe, this should correspond to a point that lies in the ordinary part, or in the ordinary locus of the eigencurve. So I'm going to call X the point on the ordinary locus that corresponds to this. And as we said, in this case, we can, the geometry of the eigencurve is a little bit easier. And in fact, we are in a good situation because, as we said last time, here the weight is 2. We are on the ordinary part. This is a non-critical slope case. The eigencurve is actually étale at this point. So this is nice for us. And the local picture is going to be something like this. Weight 2, point above it. I can even think of working, if I want to look at an infinitesimal neighborhood around it, I can think of taking the completed group ring, the completed local ring, sorry, of the eigencurve at X, and identifying it with the one of the weight space. So in practice, I can think of this as just a power series ring in one variable. And I'm going to call this guy lambda for simplicity. Notice that this is different from what I called lambda at the beginning, which was the Iwasawa algebra, which was over similar but over ZP, which makes a significant difference in terms of points. Okay? Hmm?
Usually you take integral and then invert it.
It's not the same. That's
okay.
right. This has 1 point. That would be, yeah. So I really want to work here and not worry about it. Okay. Great. So under this formulation, what we want to do is essentially thinking of the morphism from the abstract Hecke algebra that will land by composition in lambda and compute the image of UP under this morphism. This is not really possible to do in full, but we want to compute a derivative. So we want to maybe quotient by x squared and determine this composition. Inside here. I'm going to call this variable epsilon to just emphasize that I'm working infinitesimally here. Okay? And now we want to use this connection with Galois representations that we've established. So this is the big idea in the proof of this result. Once you reduce it to this question about derivatives of operators, we've mentioned at the beginning of this lecture that the that the value of the UP operator in the ordinary case is encoded in some way in the Galois representations of ordinary forms, because those come with an unramified quotient on which Frobenius acts by UP. So that's what we want to use. So what is the Galois representation attached to this guy? So let's look at the Galois side. So I'm going to take rho to be the Tate module of the elliptic curve tensor by QP. So that it becomes a vector space. And okay, so it's the Tate module, but we want to use our split multiplicative reduction setting to understand the Tate module when we look at as a Galois module for the action of the composition group at P. And it turns out that in this setting, we have that this guy, maybe I call it B, and I call rho GQ GR. This guy sits between QP twisted by 1 and QP. So it's an extension of the trivial representation by cyclotomic, which means that if I choose my basis when locally, when rho restricted to GQP corresponds to this, meaning that in practice, once I choose my basis, this will look something like this. Yeah? Just prefer to write it this way, because if I write it this way, I can identify the C with a cocycle. It's going to be a cocycle for the quotient of these two characters. Everything is local at P here. Okay? So now we are in a nice setting because we want to describe cocycles for this, but we can't say a lot because this can be interpreted in terms of Kummer theory. Okay, so how do we interpret that in terms of Kummer theory? Well, this is a calculation that uses the Tate parametrization. That's really the input. as a cohomology group, this can be identified with QP units. This is tensor with completed tensor with QP. And here, if I want to understand that extension, right there, it turns out that C corresponds exactly to viewing my parameter here, QE, inside this group. This is, if you haven't seen this before, I'm happy to discuss it in the discussion session. Okay, so we're going to take this as an input. Great, so what is the point that I'm trying to make? Well, now, because it turns out that I can actually construct a Galois representation valued in lambda, in this case, which is not entirely obvious, but the modulo x reduces to rho. And that this is also, it turns out, ordinary in the sense that I described before, so that it has a sub that is stable under the decomposition group AP, and the quotient, I can try to compute what I get up to first order. So I'm going to think of this, reduce it mod x squared, and look at this inside GL2 through P epsilon. And get a representation that will look like something like this. So a priori, these guys, eta 1, eta 2, and eta 3 are just functions, but I'm going to say more about them. Eta 1, eta 2, and eta 3 are functions from GQP to QP bar. But what can we say about them? Well, if we want this to be a representation, so a group homomorphism, then the ones that appear on the diagonal entries have to be homomorphisms. Eta 1 and eta 2 are homomorphisms So I write this as the cohomology group H1, QP. QP. Hmm?
Is there an omega p? Hmm? Is there also an omega p missing at the upper right?
Here? Yeah. Thank you. So rho lambda over lambda, maybe the composition I call rho epsilon. Because I never said it.
You need it to be global.
Hmm? So,
is it important that it's a representation of G of Q, or you just can work with it?
In this computation, it isn't super important, but
because you always describe it locally.
Yeah, this is.
It is true that it's global.
Yes, it is true that the whole thing is global. But this is a crucial difference between what I'm talking about now and what I will be talking about later. This computation is entirely local, but there will be a global one next, hopefully, if I get there. So, okay. what is the point of everything? So we have this extension class that corresponds to a class in cohomology. We have these two guys that land in this group, cohomology group H1, QP, QP. Fine. The crucial thing is now, if we want this to be able to fill this upper right corner in such a way that this is a group of homomorphism, which it has to be if it's a representation, then this corresponds to a condition in cohomology that I'm not going to write super explicitly, but it corresponds to saying that a certain cup product vanishes in cohomology. Certain cup product between the class involving the class of C and the two classes in here vanishes. But this is going to be a cup product between H1Q QP and H1Q P. QP twisted by 1, landing in H2 QP QP1, which is the setting of local state duality. And our class C corresponding to my parameter, it lands in here. What is this guy here? Well, this is GQP QP, which I can interpret in terms of local class field theory. So I can also view it as QP QP, QP units to QP. What is the basis of this space? Well, this is going to be, you can take this to be the logarithm, the p-adic log, and the p-adic valuation. And this, we said, corresponds to the element QE in QP units. So the ratio of evaluating log or P at the parameter is exactly the L invariant that we're looking for. And this is how the L invariant shows up in the calculation. Okay? So this is going to be our motivation to consider derivatives more generally, and hoping that we can connect them, no, maybe I'll use the other boards, with the theory of Galois representations in other settings. So note that crucially this was a calculation that was completely local at L, at P. Can we try to extract the derivatives of systems of Hecke eigenvalues for other Hecke operators? So in general, the question is quite hard, but there is a special case that has to, that is the setting of weight 1 modular forms in which this is actually possible, and that's what I'm going to try to talk about now in a specific example. So. Part 2, one Eisenstein series. Okay, so in this setting, there is actually this understanding the geometry, the eigencurve in this setting is actually very much related to another instance of special, like an exceptional zero conjecture for a p-adic function. So there is a parallel between the two, although it's not a perfect parallel. So let me start by fixing phi, a Dirichlet character. Of level n. I'm going to view this both as a Dirichlet character and as a Galois character. And to this guy, we can attach Eisenstein series, just like we did in the first lecture of this lecture series, up to modify the coefficients a little bit. Importantly, I want phi to be odd, which makes me want to consider the odd weights, okay, instead of the even weights, as I did the first day. So same thing, sum over the divisor functions multiplied by phi of d, q to the n. So as we've seen, if we modify things at p a little bit, so that we sum over the divisors that are prime to p, this actually interpolates nicely. We, of course, have to change this guy too. Turns out that what is interpolated when we change that guy is called the p-adic function of phi times tau, where tau is the Teichmuller character, but it doesn't matter, it's just a choice of convention. To get the correct interpolation. So this makes sense for k equals 1 as well. There is also another option of swapping the roles of the two characters and getting another Eisenstein family. In which the coefficient for the constant term is going to be 0, and then we get a similar sum with the difference that now we're going to take d to the k minus 1 phi n divided by d q to the n. And again, we can do the same business of removing the divisors of n such that p divides them, and this interpolates p-adically. So this interpolates to a family that I'm going to call E phi, no, 1 phi, and this is E phi 1. So the interesting point that I want to make about these two families is for weights greater than 1, the classical Eisenstein series, before I remove p, are genuinely different. But it turns out that if you look at the case of weight 1, the two classical Eisenstein series literally coincide. Yeah. Yeah.
These are definitions, right? I mean, you define now two variables, 1 and 5.
Yeah, characters. One is, yeah.
Yeah, okay.
Yeah. Yeah, I need to keep track of which one. Okay? So the two families, if you check what the contribution at p is, looking at this condition that p yeah, well, these two are equivalent, of course, that P does not divide D, are characterized by different values of the UP operator. Yes?
How did you get the first Eisenstein?
So that would be a p-adic interpolation. Yeah. So it's a notation for now. The claim is the whole thing does interpolate. And there is a p-adical function that is characterized by this interpolation that gives you the constant term of this. So take it as a definition. But thanks. OK. So some interesting things about them. So for P1, get the UP eigenvalues if you check what is left after removing the divisors that are divisible by P is 1. And for, no, sorry, different. And for the other ordering, got the UP is equal to phi p constantly across the family. So this is fine, and for weight k greater than 1, doesn't cause any problem. For weight 1, since the system of Hecke eigenvalues away from P already coincide, we actually have that if these two, we have two possibilities. So if phi p is different from 1, then we have two families parametrized by the weight space. But if they're equal, which might very well be, you can take such a P, the weight 1 specializations are equal. Which makes sense in this case, if you think about it. If I take the family, so I can take E phi 1, the weight one, yeah. P is prime to n, yes. Yes, P is prime to n. So it turns out that, so if I take, I don't know, by G E 1 phi, and I'm now going to stick to the setting in which 1 is equal to phi of P, and I'm going to denote as G alpha the unique stabilization at P of level with P in the level. Then this corresponds to a point on the eigencurve but we know that because there is a unique stabilization at P, we've already observed that when we look at the generalized eigenspace corresponding to the system of Hecke eigenvalues of X, then this is not one-dimensional, because this is not equal to the span of this. Because at the very least, it contains the element G as well. So this will be a general, G, the non-stabilized version, is a generalized eigenvector, which already tells us that the eigencurve is not étale, and indeed we found two families. Is that all? Well, the answer is no, for two reasons. So there are more families. Through X. One is, one reason is, okay, I can look at elements of this generalized eigenspace, but if that were actually the whole picture, we would see that a basis would be given by this element G alpha, and I could take another element to be given by, I'm going to take view the families as with coefficients in lambda, because they are parameterized by the weight space. Take their difference and take the derivative. I could do this. This would give me a generalized eigenvector in that space, but the span of this does not contain this guy here. That has to be there as well. The other, more conceptual reason is that actually, if I look at this stabilized G alpha as a p-adic modular form, a p-adic over convergent modular form, as an over convergent modular form, is cuspidal, which is a real subtlety that appears when working with the eigencurve, that things that are classically Eisenstein series can become p-adically over convergent cusp forms, meaning that their Q expansion does not vanish at all cusps, but it vanishes all cusps that lie in the multiplicative part of the ordinary locus that we described in the very first lecture. So you just get half of the cusps, and the constant term vanishes at all of those. So this is actually telling us that there will be at least one cuspidal family through it. So there will be a F cuspidal family. Okay, let me think about what I want to say, because obviously I don't have time to say everything I wanted to say. Right, so what can we say about the coefficients of this cuspidal family? So this is a setting in which there is a special value, an exceptional zero conjecture, which has been a theorem for a long time, that involves now a different p-adical function, which is exactly the one that shows up as the constant term of the first of the two Eisenstein series that I've written down, which has a very similar shape, though, to what we had before. This is a theorem of Ferrero, Grimberg, and Gross, which is an instance of the first instance of what was later called the Gross-Start conjecture, that tells us the derivative of this L function, phi tau, at s equals 0, which is the relevant point for us, is going to be equal to the classical L value of the character phi, which would appear as the constant term of the non-stabilized Eisenstein series, times an L invariant like before. This L invariant is defined as, similar to before, it involves logs and ords to normalize a certain quantity. The quantity that appears is a p unit. So I'm going to consider H the number field that is cut out by the character phi, if I view this as a Galois character. So I'm going to take Q bar phi, and I'm going to call U phi what I obtain by taking units, p units H. So this is finally generated abelian group tensored with QP bar, so to make it into a vector space. And then I'm going to take the part in which the Galois group of Q, which is the Galois group of H over Q, acts by phi inverse. So this is a representation of this group, and I'm going to take an isotypic component. One can check that using a version of Dirichlet's unit theorem, the Galois equivariant version, that this is actually one-dimensional vector space. So I'm going to take a generator, and I want to construct an L invariant out of it. In order to do that, I'm going to notice that the condition p equals 1 implies that here p splits completely. So I'm going to take p a prime above p, and I'm going to identify HP, the completion of p, with the completion with QP. And I now can view my element here in this tensor QP bar and extend log and ord the bilinearity and define my L invariant as the claim is that this formula for the L invariant is very much related to understanding the derivative arising from a cuspidal family through the point G alpha. And try to give you some ideas of why that would be true. Yeah.
Any element there is values independent of which element you're taking in this new phi?
Yeah. Yeah. Okay. Right. So, like in the case, the idea is very similar in some sense to the case that we discussed before for the formula of Greenberg and Stevens. The fact that this L invariant, if you want to prove a formula like this, you can notice that a place to find this L invariant is related to Galois cohomology. So what Galois cohomology do we want to consider? Well, if you take now the Galois cohomology of the character phi, then you can So this is a somewhat concrete group to consider because you can identify this by inflation restriction to we have the H1 of H, the fixed field by the kernel of the character, with values in QP bar fixed by the action of the Galois group of H over Q. So this is not bad now, because this is trivial coefficients. So this H1, H, QP bar is ohms of GH, QP bar. But of course, this factors through the abelianization of that. And now H, crucially, is a number field, because we started with a finite order character. So I can interpret this in terms of class field theory. So it's not too bad at all, really. Okay, so this we can interpret. Now we want to consider the restriction at the decomposition group at P of this guy. So this lands in H1 QP. Phi is trivial at P, because phi P is 1. That's where we started. So this, like before, is we can identify with just in the previous, like in the previous example, QP units, QP, and as the usual basis of log P or P. And now the claim is, if I take this guy here, turns out that this is actually one-dimensional as well. So it has a canonical generator in here. Well, not a canonical generator, but it does have a generator. And I can say that, see where it lands up to a scalar. This is a two-dimensional space. The claim is that under this map, the restriction of the C phi is equal to minus L. The L invariant that we are after, or P, plus log P. So in other words, this L invariant describes the slope with respect to this basis of the image of the C phi locally. This is a global guy, but the local image resembles the picture that we had before, and this is a computation that we can do, again, using class field theory. So why is that relevant to the setting that we are considering? So the Eisenstein series, oh, wait, one, and character attached to the pair of characters 1 phi, will correspond to the Galois representation, rho equals, well, up to semi-simplification, we will be the sum of phi and the trivial character. Right. But crucially, this is true up to semi-simplification only. And in fact, I can consider different Galois representations that give me the same semi-simplification. I can consider one that is or of the form phi 1, 0, star, and the other that is that I can consider is phi 1, star, 0. And these should correspond, as we've seen similarly to the previous example, to H1. This should be classified by this group here, and this one will be classified by this, the one corresponding to the inverse character. And in fact, so if we want to try to do the same thing we've done before, of considering a Galois representation valued in this ring lambda that corresponds to cusp forms, we can actually do that, but this Galois representation will not be unique because of the fact that we can consider different representations with the same semi-simplification corresponding to this. Nevertheless, the claim is that there is indeed a unique family of cusp forms that is valued in lambda. So there exists a family in lambda double bracket Q that corresponding to the a cuspidal family through X. And I can really pin down the Galois representation in a very certain way that corresponds to this family, because I can change lattices inside of it. But anyway, no matter what option I pick, what I can pin down is the pseudo-representation attached to it. And I can try to do, so my time is up. I can try to do the same thing I was doing before of considering this infinitesimally and getting rho epsilon here. And what is really clear that we can pin down is what this, the trace of this representation looks like, which is the same as the trace of the representation corresponding to a sum of two characters. Which are two. So like before, we are lifting phi and 1 up to first order, and we're getting homomorphisms here, which are going to be given by the composition of the cyclotomic character with the log up to some multiple. Sorry. Pair of multiples. What we need to put here is inevitably, multiple here, a homomorphism. If this is the shape of the representation, it will be a global homomorphism of GQ now, not GQP, into QP. And this is spanned by rho P of the cyclotomic character. There is only one. What are the multiples, lambda and mu, that appear? Well, turns out that similarly to what we had seen in the case of Greenberg and Stevens, these coefficients here bear a relation with the cohomology classes that would appear here and here, that classify the non-split extensions, in the sense that there is a relation that can be written in terms of the L invariance of the character phi and its inverse. There is really a symmetry between the two. But the nice thing is, so here these guys can be written in terms of logs of these p units that appeared in the previous formula. And now if I want to evaluate this trace of the representation at Frobenius at L for L not dividing P, that's actually not that bad, because if I know that the shape is this, what I have here is simply, I'm going to take the cyclotomic character of Frobenius L, that's L, and I'm going to take its log, so that's log L. And this gives me a complete formula for the trace of this representation, which in turn gives me the derivative of the L value. Sorry, can I have 2 more minutes? Is it? Oh, okay, sorry, I was...
You can finish anywhere. Wherever you want.
Okay. Oh, okay, wow. Okay, yes. Good time to stop then.
I'm a bit confused of the local picture. So the lambda
Yes.
is the completion along the family corresponding to F to that irreducible component.
So yeah, I agree. The picture is confusing. So there are many things buried into what I'm saying now. So we said that we have the two Eisenstein families. E1. The claim is that there is a unique cuspidal family that is also étale over the weight space. So I can really think of the parameter of this family to also be the local parameter of the weight space. But unlike the previous setting in which that was a like general theorem following from Hecke theory, here the argument is more convoluted because you need to prove it. And by the way, I didn't give any attributions to whatever I'm talking about. So this is a point of view this point of view related to the geometry of the eigencurve was I had considered in joint work with Adel Bettina and Mladen Dimitrov. But it is revisiting, in some ways, in terms at least of the application to the gross star conjecture, some work of Darman, Dasgupta, and Pollack, in which they also produce a formula for this derivative of the family F. But they produce that formula by hand, maybe in a way that would be maybe closer to an Archimedean setting. While part of our argument with Bettina and Dimitrov is not doing anything with calculations with forms, but using really the deformation rings to say something like there is only one shape that this representation can have, and therefore this forces there to be a unique family through cuspidal family through this point, and it must have this shape from which we can extract the L invariant as well. Okay, so what is the point of everything? Now this relates back to the theorem of Greenberg and Ferrero and Gross in the following way. So now from this formula, I can extract the derivative of the cuspidal family. And this derivative, as you've seen from the formula, so what will appear? So there will be these L invariants that know, yes?
Sorry, can I ask?
Yes.
The statement that G alpha is a classical form,
Mm-hmm. What?
why is there a classical family classified as G alpha?
So that's a good question. So the fact that it's an overconvergent cusp form is a computation on the constant coefficients at certain cusps. So that's fine. The fact that a family through it would exist is not completely obvious, just because it's cuspidal in itself. But if you think about the way we've constructed the eigencurve, we could have run the same argument from the beginning. We're constructing the eigencurve instead of using sheaves of modular form, using sheaves of cusp forms. And similar statements about the properties of the resulting eigencurve, called the cuspidal eigencurve, would work in that setting, which would tell us that we cannot have isolated cuspidal points. So if I have a point on this cuspidal eigencurve, I need to have a family through it. But yeah, that's also an interesting thing to observe, because a priori, without using this machinery, the fact that something is cuspidal over convergent doesn't seem to obviously imply that there will be a cuspidal family through it. Okay, so I was going somewhere with this. So yes, back to the exceptional zero formula. Oh yeah, so here, the conclusion was, okay, we have these two guys here that involve p units in the field H. For both of them, they lie in different eigenspaces for the action of Galois, but great, p units. And the other thing that appears in this formula when I evaluate f Frobenius L is the p-adic log of L. L is an L unit if you want. It's a pretty simple L unit, but that gives you a general sense that if you try to apply this machinery, you would to more general setting in which crucially what we used is the fact that the Galois representation attached to the form factors through finite Galois group. So the property of this being an Artin representation, you would get formulas that involve p-adic logs of some S units. This is the general idea. So here, what are we trying to say? So we were looking at this generalized eigenspace. And we said that this contains G alpha, it contains G, and it contains the x of E 1p minus E p1 at x equals 0. So the derivative of the difference of these two families there. But now I can play the same game, taking the difference of one of my Eisenstein family and the cuspidal family. The derivative itself of each individual family doesn't have any reason to be anything. But when I take the difference, I get a family that vanishes at the point, and then I can divide by my parameter x, and this becomes a sensible thing to do. So write this new derivative that maybe I'm going to take this one. As x equals 0 as a linear combination of these guys. So the argument is, okay, I'm going to match the coefficients an for n greater than 0. And then I'm going to get a relation for the constant coefficient. So this, the contribution of this family makes the L invariant appear in the formula. The contribution of this family makes the derivative of the p-adic function appear in the formula. And once you do that and compare constant coefficients, you get the trivial zero formula. Okay? So this is a specific application that one can look for, trying to write certain special value formulas, but you can have other reasons to want to construct derivatives of families and compute their coefficients. And as we said, for the setting specifically of weight 1, you'd expect those to be able to express those in terms of p-adic logs of S units in global fields. And I'll stop here.